I'm a senior lecturer at the Power and Energy Division at the University of Manchester and one of the associate directors of the Supergen Energy Network Hub. The topic of the webinar today is extremely relevant also to the upcoming COP26, and it focuses on the Flex Fund project, CLEARHEADS, climate energy modeling for assessing resilience, heat decarbonisation, and the Northwest European supergrid. And it's a great pleasure for me to introduce our speaker, Dr. Hannah Bloomfield, a research scientist at the University of Bristol, who has spent the last 8 years working at the University of Reading, studying the impacts of climate variability and climate change on national level power systems. Dr. Bloomfield specializes in modeling UK and European electricity demand and renewable generation. She has also worked on developing these tools for Mexico and multiple regions of Africa. A key outcome of her work has been to improve the accessibility of large meteorological data sets to non-specialists. The title of the talk is CLEARHEADS, Calibrated European Historical and Near Future Energy Meteorology Variables for Energy System Modeling. After the presentation, we will have a question and answer session. We can now start the webinar. I would kindly ask you to mute yourself for minimizing the background noise. Dr. Bloomfield, please, you may share your screen. Thank you.
Brilliant, thank you, Alessandra. That's a great introduction. So just to check, you can see my screen, yeah? Wonderful. Yeah, so I'm going to talk to you about some work we've been doing on the CLEARHEADS project. So this was a Flex Fund, Supergen funded project, which has happened over the course of this year. A huge thanks to Matt Deakin and David Greenwood at Newcastle. And also Ilias, who I haven't met yet, but I think is now working with us on this, and myself and David Brayshaw from the University of Reading, and also colleagues at AFRI who we've been working with, who've been giving us some great industrial input. So today, I'm going to talk to you a bit about why you need good weather and climate data. So David Brayshaw and I are climate scientists, coming at this to talk to all you lovely energy people about why weather and climate data is wonderful. So some examples from our collaboration with Newcastle, then to talk about the CLEARHEADS project. So we've been developing a data set for current and future climate, which has just come out, which we'd like to show you some details of and where you can download it. And finally, I'll just finish with some future work on the CLEARHEADS project that Matt and David and Ilias are working on at the moment. So just some motivation. As Alessandra said, COP's coming up and we're all thinking a lot about how we're going to decarbonise power systems. One of the key routes we can do this is building more renewable generation. As well as this, we can decarbonise heat, which might lead to more weather dependence and temperature dependence in our heat. We can electrify transport. There are many options, but nearly all of them result in increased weather dependence in our power systems. And this means that we really need to understand meteorological conditions that are associated with this kind of power system variability so we can get reliable power system operation. So why do I need meteorological data is what a lot of people ask me. You could just go to ENSO-E, you could go to the Elexon portal, speak nicely to National Grid, and they might give you some metadata about power system operation of various components. Well, because of this decarbonisation and our energy systems being in a period of rapid change, these kind of data sets have a lot of trends in. Every year we're building more wind turbines, we're using less coal, and that means that if you were to look at past years of data, they're not really representative of today's power system, which is really important as we start to think about particularly stressful conditions to our current and future power systems. So a topical situation at the moment that weather data can help provide us some information on. A lot of you might have heard about this summer, we've been experiencing a very big European wind drought. So there have been very low wind speeds through the whole period from around April to September. And And this nice plot from the World Climate Service from Twitter shows that actually, if you use long records of meteorological data, you can unpack this recent wind event to show you that actually this was the lowest wind period in the last 60 years. So here they've used a long gridded meteorological data set from 1960 through to present, and they've shown that the colour scale here shows actually the least windy year in orange was across this large region of the UK where we actually have quite a lot of wind generation. Across the whole of Europe as well, it was one of the top 10 least windy years through this large North Sea region. So a real challenge, and using meteorological data helps us to unpack the scope of this problem and how likely it might be to happen again. So at the meteorology department in Reading, I was part of the energy-meteorology group. And one of the key things we do in the group is provide climate data sets to energy system modelers, trying to do it in a usable way. So the key kind of process chain that I started doing in my PhD, and I've done in many years since, is to take these gridded weather inputs, so gridded weather and climate data, take some information about power system components. This might be where wind turbines are, where people live, power curves that we're interested in. And we put this information into power system impact models for demand, wind, and solar power generation. Out the end, we go from multiple gigabytes of weather data down to time series CSV files of hourly country aggregate, either weather data or energy system variables. And what I've spent a lot of time doing is thinking about the meteorological processes of interest to the power systems if you use these data sets, but others can also use these as inputs for power system models. So we've done this for lots of different meteorological tools. We've done it quite a lot for weather forecasts. So these lots of acronyms, I'm very sorry, but these first two are short range weather forecasts, so out to a couple of weeks ahead. S2S, sub-seasonal to seasonal forecasts. We've got data sets for demand, wind and solar if you want to look up to 40 days ahead. We've got reanalysis data. So this looks at historical weather and climate records over the last sort of 30 to 70 years. Or climate model data. So this is the kind of stuff that goes into the recent Intergovernmental Panel for Climate Change reports that are out. So any type of weather data, we can follow this process chain. So a bit more specifics on how we do this. So taking our gridded weather and climate data, to get from weather to energy, the key thing we do is fix a power system setup. So we might take the 2020 level of demand or the wind and solar generation that was installed at a particular point in time, and then we can pass many, many years or many, many different forecasts of weather data for that same kind of power system setup. So if we wanted to do demand, we use a multiple linear regression model based from temperatures. If we care about wind power capacity factors, we have physical models which use power curves and 100-meter wind speeds. And if we want to do solar power capacity factors, we use an empirical solar power model, which has been used in quite a few previous studies, where we take temperatures and shortwave radiation. So just an example of this, if that doesn't make a particularly lot of sense yet. So here's an example for what we did when we were looking at wind power capacity factors over GB. So here's an example done by Dirk Cannon in the group. So he took a wind farm distribution provided by National Grid. So this is September 2012, that's what we had. And we can pass all these different years of weather data from a long-term historical reanalysis product. We'll get to what that is in a minute. But then we particularly did this to unpack this really low wind year we had in 2010. So at the time, National Grid only had a few years of time series of wind power generation, and there wasn't much Dukes data either. So they really wanted to know if years like 2010 were particularly common. And we were able to unpack this a bit for them and say, actually, yeah, 2010 is a very low wind year. But it's also possible that we could have much higher wind years as we've had since then. So this is what I mean by fixing the power system setup, and we're very flexible in how this can be done. So all of the kind of data we make, we've had a big push recently to try and make it all open access. So a lot of the data is available through our research website, so research.reading.ac.uk. So you can either get yourself some weather data from there, aggregated up to national level, some demand, wind and solar data, or some kind of, and these are available for all these different kind of weather products. So there's the sales pitch, you know, go look at the data, it's wonderful. But one of the people who did this was Matt. So I don't know when it was before COVID started. It's a bit murky what year that even was. But Matt contacted us at the University of Reading and said, oh, we've seen some of your papers. We've seen the data sets online and they look good. But could we have something a bit different? You know, Matt was interested in GB, and a lot of the work I'd done was for the UK. He needed separate onshore and offshore wind data, whereas I tended to clump it all together. And he wanted a few more years closer to real time than what I've been doing. So we were, the thought was this could go into a nice study thinking about heat decarbonisation with his models. And this has since happened. So this was kind of the precursor to the project we're now working on. So I'm just going to give you some of the key results from this to get us started. So a lot of the work we've done in the past at Reading has been focused on this first speech bubble, which thinks about when you're doing power system modelling, the weather is not the same every year. And that is a really important thing to account for this different year-to-year climate variability. So within the modelling that Matt was doing, thinking about heat decarbonisation and system adequacy, we wanted to take this into account, but also wanted to think about other factors like the evolution of the demand weather sensitivities, methods for estimating how our heat demand might grow, and also this kind of heat demand profile uncertainty. So just to show what we brought to this from Reading, so we brought 30 years of hourly time series of, so Matt ran a more sophisticated demand model than I use. He used a few more weather variables and did a kind of lasso-based regression, which he can comment on later. But yes, so we provided population-weighted weather variables. So we took population data here, and we provided this onshore, offshore wind generation weighted by where the farms are, and solar power generation. So for 30 different years of weather data. This then was used as an input to a modelling framework. So Matt had some historic system demand, which formed a linear regression model using our weather reanalysis data as inputs. This then was able to be combined with our wind and solar data to kind of form this net demand hindcast. So we've got demand minus renewables as our variable here, assuming that we're going to use all the renewables we can. This can be combined with information on dispatchable generation, and then we kind of get to system margins, which was what Matt was really interested in this study. And we can start thinking about loss of load expectations and average capacity to secure. Which is what I'm going to focus on now. So this is my favourite plot from the paper because it's got lots of weather data in it. But this additional capacity to secure, what this plot is showing is if you were to use 30 years of weather data and run that all through your model, you'd come up with a number for your additional capacity to secure to make your system robust to year-to-year weather variability. The different bars here show the difference if you were to just use the 1 year of climate data. So for example, 2010-11 was a very cold winter. And if you just use that year, you would have needed nearly 3 extra gigawatts of capacities to secure, particularly if you were doing scenarios including heat pumps. Whereas say years like 92 and 93, because they're a lot warmer, quite a bit windier as well, you didn't need as much additional capacity to secure. So key points here is heat pumps led to this kind of greater weather sensitivity. And it's not just about temperature. We can see here that it's not just, the colours give you your mean annual temperature anomaly. And it's not just the very cold years which lead to the highest additional capacity to secure. There's these rogue years like 17, 18, So this is showing that actually there's more going on, and if you unpick this, it's actually quite windy in this year at your times of peak demand. So it just shows it's all a bit more complicated than just thinking about temperatures. Another plot that's really nice that came out of this is unpacking the different uncertainties in a bit more detail. So the thing I was really interested in here is the weather uncertainty. So this is, so there's two different modelling frameworks used here. I think NGESO is a kind of low duration curve based modelling framework. Matt can correct in the chat if that's wrong. But the explicit model is when you're explicitly modelling your kind of changes in how heat might decarbonise over time. And we see here that if we just look a year ahead to the 21-22 winter, weather's a big deal. The additional capacity to secure is really impacted by the choice of weather years. Whereas going forward a bit more, weather is still going to be quite a big issue in say 24-25. But it's also impacted by these different heat pump scenarios we had. So these were different diurnal heat pump profile curves, which we can talk about more in the end if people are interested. But key thing we wanted to show people with this is that, you know, whether GB temperature demand sensitivity could change a lot in the future. Matt found that it could increase by 54% in just 4 years. And electric heat demand growth uncertainty doubles your variability and capacity to secure. Basically, we kind of finished this modelling, and we thought it was really interesting. The weather data had been quite useful, and we'd unpacked this for GB in quite a nice way. But then the kind of idea for the project we're currently working on was born. So CLEARHEADS, the ridiculous acronym, Climate Energy Modelling for Assessing Resilience, Heat Decarbonisation and the Northwest European Supergrid. It's clutching at straws a little bit to get to CLEARHEADS, but yeah. The key thing we wanted to do is extend this work. So rather than just looking at GB when we're thinking about times of stress and maybe problems with adequacy, we're extending this out to look at what we're calling this Northwest European supergrid. So many more countries, including things like interconnection between the countries, more years of past climate data. So previously Matt was using 30 years. We're going to extend this up to 70. Thinking about the impacts of climate change, so using multiple future climate projections, and thinking about lots of different decarbonisation scenarios. So that's the project we've been working on, and is still running till December. But the things you can get out of this, we're making all of this weather and climate data available for a present and future climate. We're providing scripts for how we process the weather data. So if you don't like the way I did it, you can do it again yourself. And Python libraries as well for calculating useful energy indices like outages, which we'll talk about in a bit. So now I'm just going to take you through the data sets we've been making and give you a bit of an overview of what we've been working on. So meteorological data. For our present climate, we are using the ERA 5 reanalysis. So this is a historical weather product, which has a spatial resolution of 30 kilometers and hourly resolution. So this is pretty state of the art if you want to look at your past climate data. And that runs from, it's been extended recently, so it's now going from 1950 through to present. So as well as this, we've looked at the output from 5 different future climate simulations. So these are all high resolution climate models. Note that if you're interested in global climate model simulations, high resolution means 100 kilometers. It's very computationally expensive to run these climate model simulations. So spatial and temporal resolution is a big issue. We took a real push here to find hourly simulations, and then we had some free hourly to top it up. Just to note, very little hourly future climate data currently exists. So for energy modelling, I know that's what you want and what you need. And yeah, we're working on methods to make as much of that available as possible. So the key thing we do is take all this model data from the grid and turn it into these kind of time series. So I've said this word a lot, reanalysis. I'm now going to tell you what it means. So reanalysis is what we kind of call our historical weather products. So a reanalysis is a weather model which we run to include all of the past observations. So with a standard weather forecast, you have your initial state, and which will include the best observations you've got at the time, and then you can just set it off running in time and you get a forecast. With a reanalysis, we run it back on historical data. So we can clean up the observations, include data that wasn't quite ready at the time of the initial forecast, like satellite data, all available observations. And then we use this technique called data assimilation to fill in any gaps we've got in the observations using information from nearest neighbours. So you can kind of think about this like this nice graphic here, like a puzzle. So you can see we don't have very good global observation coverage. So this is just the point-based observations. We've also got satellite data as well to top this up. But you can see there are gaps and places where our gridded record wouldn't be quite so good. So here what the reanalysis is kind of doing is it's looking, if it were to be a jigsaw puzzle, it's looking for the best way to fill in that piece in places where we don't really know what was going on, through using the observations and combining that with the weather forecast model. So what we use a lot in this study is the ERA5 reanalysis, which I know a lot of other groups use as well. So this data set runs from 1950 through to present and gives you hourly gridded weather data at multiple heights through the atmosphere. So a really good resource. For our climate model data, we take data from the Primavera project. So this is high resolution global climate data. So a new generation of climate models. This was really pushing the frontiers in terms of spatial and temporal resolution of the outputs. So if you use climate data already and you'd like to get your hands on some of this, you can either download it directly from ESGF, which is a Earth Science data platform, or you can download it from the Centre for Environmental Data Archive, or access it directly through the Jasmine supercomputer. So I will note that to get our hands on particularly the solar data, we had to put in some bespoke requests to the Primavera project, because they archive a lot of this data on tapes and kind of pack it away because not many people are using it. So we did have to put in some requests, but a lot of it does exist. So we processed about 4 terabytes of climate data for this project and got it down to a few gigabytes of time series. So this is one of the big challenges with using large amounts of meteorological data. It's huge. You need somewhere to put it, and it takes quite a lot of time to process everything. So hopefully what we're doing here is useful to show the methods and the code we've used to do this. So calibration of the climate model data. So this is quite important. We're using these 5 different future climate model simulations, and it's, you know, it's very unlikely that if you were to take a climate model off the shelf and look at the output, it would look exactly like the ERA5 style observations. The models often contain biases, so maybe problems with the mean or the variance of the data. So what we tend to do is various methods of bias correction to make sure we've got a bit more faith in the data that we're going to use. So just as an example here, I've tried to make a bit of a picture of what we're doing. So here we've got some PDFs of 2 meter temperature, so just probability density. So for the observations, we might have a PDF that looks like this black line, and the model for the same period. So if we cared about, say, I don't know, 1980 to 2020, it might have a slight warm bias. And we're like, okay, the model's a bit warm. We can then look at a different period in the model. Say in this project, our future climate period, we're using 2020 to 2050. So we can look at this period and see how much the model is warmed. And this is what we call our kind of climate change signal. So I've just got an example here for the EC Earth model in winter. So we've got the present and future, and then we can get the climate change signal. And unsurprisingly, you can see here that it's warmed by kind of 1 to 2 degrees over Europe in this time, depending on where you are. So what we chose to do in this project is to use a delta correction method. So what that does is it takes this climate change signal and applies it to the ERA 5 data. So what we have is a full set of our past observations with the impact of climate change applied to it from 5 different models. Why do we think this is useful? Well, it allows you to look at the impact of climate change on past events that we know has happened. So for example, if you care about, say, the Beast for the East in 2018, you can look at what would have happened within that event in a warmer climate, which might have different wind and solar responses. So yeah, it also makes it easier for processing the different years of data. Climate models have some quirks. For example, the Met Office models only have 360 days in a year. So that leads you to some adjustments needed to be done in your code. So we avoid this by doing this delta correction method. So we don't just correct the mean, is one of the key things we're doing here. We apply this delta correction seasonally and also to all the percentiles of the climate data. So let's just take an example for a grid box here in Helsinki. So what we've got here is the kind of cumulative distribution function of 10-meter wind speeds, one of our variables. So you can see that the cumulative distributions are quite different per season. So winter is in the blue where it's most windy, summer in the red. So what we do is for that grid box for each season, we calculate this CDF in the present and the future climate. So the most obvious one here is the winter one. The dashed line is the future climate and the solid line is the present. So you can see this change has occurred and we apply that change to the CDF of our historical observations. So we've done it on the whole distribution because in this project, we're interested in times of power system stress, and these tend to be at the extremes of a distribution. So this means that every different part of the distribution is getting its bespoke correction. So when it's very thorough, like with how many different bits of the distribution you're changing, but hopefully it should mean we've got realistic behavior at the extremes. And just to give you an example here of why we are using 5 different models, you might think, why do I need 5? One will be enough. Well, all of the models have different magnitudes or sometimes even directions of response to climate change. So for temperature, all of the models warm, but the amount they warm differs depending on which simulation you've picked. Whereas here, we've got some examples of 10-meter wind speeds for 2 different models, the top and bottom rows for the 4 different meteorological seasons. And you can see if we just focus on winter here, in this bottom model run from the UK Met Office, we actually get it getting a bit windier in winter over the North Sea and parts of France and Spain. Whereas in the European Community Earth model, we actually get either no change, the dots mean there's no kind of statistical significance, or we get some reductions in wind speed up here. So there's no reason to think any of these models was more or less plausible because they all have a good representation of our current climate, so they're good models. Wind is just difficult. There's a lot of different possibilities for how winds could evolve in a future climate, and we're hoping to capture some of this within our 5 different simulations. Okay, so that's how we do all these bias corrections to the gridded data. Now I'm just going to tell you what variables we create. So within the data set, we have national and subnational scale meteorological variables. So we have 2-meter temperature, 10-meter wind speeds, 100-meter wind speeds, and surface shortwave radiation. We also create wind and solar capacity factors at national and subnational level, and some heating and cooling degree days. So the external data that comes into this, as well as the climate models, all of our weather variables are also available in this kind of population weighted format. So if you're modeling demand, this might be a lot more useful to know about the temperatures where people live. Whereas for the, excuse me, for the wind and solar models, we create data sets that are weighted based on where we know the wind farm and solar panel locations to be. So we use the windpower.net for the resource for the wind farm data, And for solar panels, we use the Dunnett et al. Data set, which is open access, and it's a global resource. And we top this up over the UK with an open climate fix data set, I think, from Stowell et al. So now I'll just take you through how a couple of these models work. So our wind power generation model, which we've spent quite a lot of time trying to refine the technical details of, but yeah, so the key input here is hourly ERA5 data, 100-meter wind speeds go in. We apply some pre-calibration just based on our meteorological experience. We know that ERA5 sometimes isn't windy enough, so we apply some correction based on a global wind atlas product we have. So we take these 100-meter winds and we have them over all of the grid boxes over this region of Europe. And then we extrapolate them down to where we think an average wind turbine hub height would be. So if it's onshore, this is about 70 meters, and offshore is about 90. And this is just from us taking all the locations of European wind farms from the windpower.net. So this is based on where real current farm heights. So we've then got these wind speeds at various heights for onshore and offshore. And we pass them through these power curves. These are taken from a national grid report. So we have the onshore power curve in red and onshore in black. We can then aggregate this data. So it's still on the grid at the moment. We can aggregate it to national level based on the amount of wind power generation we know is installed in each grid box. So for example, in 2021, in our database, we've got 12.6 gigawatts of onshore wind and about 10 of offshore, which is relatively close to what's actually there. So yeah, aggregate this up, and the output is time series of national capacity factor. One thing that's available from the windpower.net database for a source is the planned generation as well. So as part of the data set, we've also got a future distribution, which the onshore is pretty similar here. So these are the two plots you saw before with the onshore and offshore wind. But the key thing is there's this offshore planned generation for GB, which goes out to kind of nearly 30 gigawatts. So for every country that we've modeled over Europe, we've got a version for the present and the future wind farm distribution. For the solar PV modeling, we take gridded 2-meter temperatures and surface solar radiation, and these go through an empirical model. So the capacity factor of our solar panel, calculated in each individual grid box, is the ratio of the power that we've currently got to the power at standard test conditions. So the way we calculate this is we take the shortwave radiation at the surface as a ratio of this, the shortwave that would give us the best solar power output, and we multiply that by this efficiency factor. And what the efficiency factor does is just accounts for the fact that as it gets a bit warmer, the solar panels get a bit less efficient. And this is kind of shown here that for higher irradiances and higher temperatures, you get a bigger knockoff from this optimal 1-1 line. So one thing you probably want to ask is, are these models any good? And over the course of the year, we've been checking that they are at least reasonable. So an example at the top here for the GB onshore wind power generation for 2018. So the black line is the measured data that we got from, I think this is from Lexon, and the green line is our simulation. So you can see we're doing a pretty good job, very high correlation. Seen with these time series, a couple of problems with the magnitude occasionally. But this is a purely physical model. We're not trying to account for any curtailment, so we're pretty happy with this. At the bottom, we've got an example for solar PV. This is GB, not UK, sorry, bad label. Solar is a bit harder, but still we have very high correlation. We just struggle with some of the peaks. I think this is due to the historical model's ability to represent the clouds at various locations. But still, the correlation is very good. And because we're outputting capacity factor, you could scale this to your installed generation output to slightly perfect the result. So the regions we've created this data from, this is something that they've really pushed me on actually compared to what we used to do. We used to just do this national level data. So now across the UK, we've also got NUTS 1 level. So I can't remember what NUT stands for, nomenclature units, territories, something like that, but basically sub UK level data. And in Scotland, we went down to NUTS too, because just having Scotland all as one individual zone didn't make a lot of sense. The shape files to do this for all of these zones are freely available if people wanted to recreate this. And for the offshore zones, so we calculated the amount of wind power generation in all the European countries' exclusive economic zones, because we were thinking about physically where might it be possible to build a turbine, even a maybe very futuristic turbine that doesn't need very deep oceans, it might be floating. They could go anywhere in this region. And for around GB, Ireland and Norway, we also created smaller data sets which were related to the UK Met Office shipping zones. We did these because they match quite well to where wind power generation actually is built. So we'll talk about this later. Another data set that's coming out soon, which Matt has been working on, is thinking about power system outages. So this is data which is took quite a bit of processing, but generally, why might we care about this? Well, in the short term, you might want to understand your distribution of your loss of load. You thinking further ahead, you might want to think about, maintenance scheduling of power systems or long-term availability of generation assets when we're at times of peak. So this was going to be an important part of our project to think about these outages and how they interact with the wind and solar generation. So Matt's been processing this data a lot. We have some planned outages in blue, I guess, which is associated with maintenance. And we also have forced outages that happen. And the total here is in black. So Matt's been processing this a lot. And you can actually see that in terms of the outages, different countries have very different patterns. For example, in France or GB, you get peak outages happening in the summer months. Whereas in Spain, you get this kind of biannual minimum. So here we've got data from 2017 all the way through to 2020. So there's a few years of cycles going on here. And you can relate this. So if you see your outages, you see in some countries it relates quite nicely to the demand outturn. So for example, Spain has peaks in midsummer and midwinter, but has like a lower seasonal demand when you can look at this kind of biannual outage data. So coming soon to this is Matt's been working really hard making a GitHub repository of the scripts to automate the download of this outage data. It's quite a messy job. So he's worked out how to do this efficiently, how to post-process and aggregate it to a country level and estimate the uncertainty due to this. There's a lot of conflicting reports, I think, and there's a lot of missing numbers, and yeah, spent a lot of time processing this. So that will be coming soon as well as part of the project. So a few quick examples of how to use the data before I finish. So we mentioned these offshore wind zones that we've been creating. So I just want to show you an example here of the winter 2020 cold snap. So if you were to just look at the UK total data in the black line, you'll see we had some quite big ramps in wind power generation through the 23rd to 31st of December. But if you actually unpack 3 different zones here, so Cromarty in blue, the Irish Sea in red, or the Thames in green, so they're all regions where we have a lot of wind power built. You can see some really striking ramps happening. And particularly in the Thames here, actually there was a ramp up in generation while the national average was going down. So in terms of grid balancing, having these sub-national data sets really useful for understanding some of the kind of smaller network challenges. So something else that Matt's been working on is because we have this data in all these regions, this is a map from the Met Office just showing you the names of all these shipping zones that we've processed. You could actually start again and kind of hypothetically think, where would it have been best to build our wind power generation? And one of the games that's been played is, can we maximize the minimum of seasonal capacity factors? So if we wanted to do this, it turns out if you just wanted to maximize generation, you would invest all of your money around the north of Scotland. So that's great. We could increase our seasonal capacity factor quite a lot compared to if we just invested uniformly around all of the regions. But then we see if you do this, you get some key problems. For example, the optimal like long-term setup for the mean capacity factor results in some quite substantial wind drought periods, because if the generation isn't spread out so well as around GB, you're more vulnerable to these areas of kind of localized high pressure. So another interesting thing you can think about with the wind data. Just a quick example, thinking about the impacts of climate change you can unpack with this data. So there's two examples here: a very cold winter, the big freeze of 1963. So the black line is our observations, and all the different coloured lines are our climate change simulations of that event. And the key thing I want to pick out here is if an event like that were to happen in a future climate, be much less likely that we'd spend a whole day at sub-zero national temperatures, which, well, must have been incredibly problematic this whole period at the time. Another thing to think about is heat waves. So again, the black line at the bottom here shows our 2003 heat wave event. And we see that in a future climate, this event would have been, if it were to have occurred again between 2020 and 2050, would have been much warmer, and we'd have multiple days in a row with national average temperatures of over 30 degrees, which potentially would cause problems for providing cooling water for power plants and also huge air conditioning scale demands. I'm going to get through this one quickly because I want to leave some time for questions, but you can also use these kind of data sets to think about compound events. So for example, we've looked in all the different climate change simulations. How many extra hot days would you get per year in the different countries for a future climate? How many hot and still days might you get? So this is if you're thinking about maybe summer wind droughts, and then maybe hot and cloudy days. And you can see the different return periods of these events here. Yeah, lots of different games you can play with the data, and we'll be bringing out a data paper soon with some of these examples that I've shown, but if you want to look in more detail. So I like to put this plot in when I get near the end, because I think if you're not used to using climate data, it can feel like the climate scientists turn up with this truck full of data, and you're just a bit like, oh my goodness, I'm not really sure what to do with this. But our hope is that we can try and fill this gap a bit between the climate and the energy science through providing this data processed into time series that can go in your folder and hopefully be used as a useful input for any kind of work you might want to be doing. So if you want to access these data sets, head over to the research data at Reading Archive, either just the historical data or the data including the impacts of climate change. It's all there. It doesn't have DOIs yet, it's just got these links because we're waiting for the data paper to be accepted first. And when you get to the website, it looks a bit like this. You'll kind of get to this portal, and you'll be able to download in zip files the time series for the various different things you might want to download. I would highly encourage getting the README first, because all of these zip folders are quite big. They're all about between 500 megabytes and a gigabyte. So if you just download the lot, your computer, well, might get quite full quite quickly. So future work, the data's been made and the project is still ongoing. Matt, David and Ilias are still working hard using this data. And three key things that they're going to think about using this data is decarbonising heat, evolution of renewable sensitivities, so more wind and solar, and increasing interconnection. So you're going to be thinking across this whole Northwest European supergrid region, but also doing something a bit more focused with our GB subnational data to consider how our system extremes might evolve. So I think this is my final slide, but yeah, the key thing we're thinking about, which is quite difficult actually, is this heat decarbonisation. So all the systems across Europe are currently very different. You can see an example here that the UK has a lot of gas, and the green is electricity and the grey is oil. So UK has a lot of work to do, so does the Netherlands and a few other countries. But Norway, for example, already has a huge amount of electric-based heating, so not so much changes to do here. So potentially one of the things Matt's going to do is to take this data set from Maria Victoria and Tom Brown, which has just come out, looking at possible evolution scenarios to decarbonize heat, how we get from this large amount of gas boiler through to something a bit more heat pump based, and incorporate our weather and climate data into these changes. So I'll leave my summary here because I've talked for a long time, but thank you very much for listening, and please do get in touch or ask questions now if you've got any questions. Thank you.
Thank you very much, Hannah, for the very interesting presentation, and also for making these data sets available, because it's very much appreciated. I think that they have a wide range of possible applications.
Yeah.
Thanks a lot. Thank you very much. Yes, I would like to open the floor for questions. You can either write your question in the chat, I can read it for you, or you can raise your hand and unmute yourself and then talk when you are invited to do so.